Hello class, today we are going to continue with chapter 6.3 looking at cubic and quartic functions. So a cubic function in the variable x has an equation of the form f of x equals ax to the third plus bx squared plus cx plus d with a not equal to 0. It is characteristic of a cubic polynomial function to have a graph that has end behavior that can be described as one end opening up and one end opening down. The specific end behavior is determined by the leading coefficient, the coefficient of the third degree term. The curve opens up on the right if the leading coefficient is positive and opens down on the right if the leading coefficient is negative. In general, the graph of the polynomial function of degree n has at most n x-intercepts. So cubic function might look something like this. Like I said, this would be a positive coefficient because the right endpoint is up. Could as well maybe look something like that. This would be where the coefficient is negative. Could have at most n x-intercepts. Okay, so the cubic function, so if it hits the x-axis, it could hit the x-axis at most 3 times. 1, 2, 3. Doesn't have to hit the x-axis 3 times. Might only hit it once. Might hit it twice. But hits at most 3 times. So you can have at most 3 x-intercepts with a cubic function. Alright, the graph of the cubic function will have 0 or 2 turning points. Okay, these turning points are called the local extrema points of the graph of the function. In particular, a point where the curve changes from decreasing to increasing is called a local minimum point, and a point where the curve changes from increasing to decreasing is called a local maximum point. The highest point on the graph over an interval is called the absolute maximum point on the interval, and the lowest point on the graph over an interval is called the absolute minimum point on the interval. Okay, so if you've seen the cubic functions that I just graphed, it could look something like this. Your maximum is the point at the top, local min is the point at the bottom. Okay, now absolute maxes and absolute minimum points vary because if we look at different ranges, what we call the local min and the local max might not necessarily be the absolute min and the absolute max. So if I looked at the graph from here to here, and that was my range, my absolute max might actually be right here, whereas my local max is just right there. So that's absolute max versus local max. Same thing with local min. My absolute min might be right here, whereas my local min might not go as low. Okay, can be the same, but in some cases, depending on the interval, it's not. All right, this says use an appropriate viewing window. Let's graph y equals x to the third minus 27x and find the local min and local max if possible. Okay. Now, if you put that in on your TI-84 calculator, you'll put that into y1. And if you put that into y1, you can use the second calc function and look at the local maxes and the local mins by bounding them to the left and the right. You just have to get your viewing window appropriately. Now, you can use the viewing window that they recommend here that kind of meets the graph over here on the right-hand side. The viewing window is negative 40 to 30 and negative 100 to positive 100. Okay. So your x values are ranged basically here from negative 30 to 40 and negative 100 to positive 100. Now when you find these extreme points, like I said, you'll basically do second calc and then you'll find either the min or the max. Depending on what you're looking for, you'll left bound it, right bound it, and then guess. Hit enter again. You'll find it for you on your TI. If you struggle with TI calculator commands at this point, send me an email. We'll see what we can do to help you figure out those calculator commands. Plenty of videos on YouTube that can help you with those as well. But the calculator will calculate these mins and maxes for you. All you do, put it into Y1, graph it. As long as you can see it, you can find it. Okay, if you find it, you'll find that your local maximum here is negative 354, and your local minimum here is 3 negative 54. Okay, we have 2 local extrema. Now, next thing it's going to ask you is, it's going to ask you what is the absolute maximum of this function on the interval from 0 to 3. Okay, now from 0 to 3, let's go back and look at the picture. 0 to 3. So from here to here, what's your absolute maximum? What's the maximum point between here and here? Well, it looks like it's right here at 0, 0. Okay, we're not talking about the local max here. We're just talking about the max on the small allocated interval from 0 to 3. On that small allocated interval, our absolute max is 0, 0. Okay. Let's look at quartic functions. A polynomial function of the form f of x equals ax to the fourth plus bx to the third plus cx squared plus dx plus e, where a is not equal to 0, is a fourth degree or quartic function. The basic quartic function has the graph shown below. Almost looks like a quadratic. Now, a quartic function doesn't have to look like that. It could as well look something like this, or it could be flipped the other way, or it could be flipped the other way to look like this. Okay, and it's not as pointed right there. It's more of a rounded curve like that. Drawing's not the greatest. But you kind of get the point. So quartic functions. We got some definition based on quartic functions here. The end behavior of a quartic function can be described as both ends opening up if the leading coefficient is positive, or both ends opening down if the leading coefficient is negative. Variations in the curvature may occur from different quartic functions, but these are the only possible end behaviors. So for a quartic function, you either got both ends going up or both ends going down. Okay. Now for polynomial graphs in general, so cubic, quartic, quadratic, whatever it might be, for any tile polynomial graph, we have some properties here. The graph of a polynomial function of degree n has at most n minus 1 turning points. The graph of a polynomial function of degree n has most n x-intercepts. The graph of the polynomial function with odd degree can be described as one end opening up and one end opening down. And the end behavior of the graph of a polynomial function with even degree can be described as both ends opening up or both ends opening down. Circling back to 1 and 2, we kind of already looked right there on the cubic function at how many times it could cross the x-axis. Same thing for quartic. If we go back to it, you see it could cross the x-axis at most 4 times. Might only cross it 2 times, depending on how it's drawn. So here we can cross it 1, 2. Could cross it 3 times, could cross it 2 times. But at most, might cross it at all, depending on how the graph, the x-axis is here. This one doesn't even touch the x-axis. 0 to 4, right? But it can have, if you look at number 2 here, the graph of polynomial function of degree n can have at most n x-intercepts. Okay. And then it can have n minus 1 turning points. If we go back and look at the turning points here, it can have at most n minus 1 turning points. So if you look at the 4th degree, it can have at most 3. That's n minus 1. 4 minus 1 is 3. It can have 3 turning points. Here it does. 1, 2, 3. This one only has 1 turning point. This one only has 1 turning point. This one has 3. Okay. So we're looking at the at most part here. Could have at most 3 turning points. So let's look at these graphs here and see if we can identify the lowest degree polynomial we can estimate them with. So let's first look at the number of x-intercepts. How many times does it touch the x-axis? Well, it touches the x-axis right here and right there. So 2. Now let's look at the number of turning points. Well, we were going down and now we're going up. We've got 1 turning point right here at the minimum. Now, is the leading coefficient positive or negative? Well, this one has both ends going up, so it's positive. Okay. And is the degree odd or even? Well, if the end behavior is the same, then the degree has to be even. If the end behavior is different, that's when it's odd, but here it's even because the end behavior is the same. Now, final question, what's the minimal possible degree here? Well, based on A and B, and the way the graph looks here, looks like the smallest degree could be a 2. I could estimate this with a quadratic. Could be a quartic, but the smallest thing that I can estimate it here with would be a quadratic. And I base that primarily on A and B. Because the smallest number there that it could be is a 2. Couldn't be a 1. 1's linear. Alright. Complete the graph of the polynomial function is shown. Let's see. Let's determine the number of x-intercepts here. Okay. Well, we've got 1, 2, 3 looks like. Let's determine the number of turning points. Looks like 1, 2, 3 on that as well. Leading coefficient positive or negative? Should be negative because it's going down, and it should be even because both are going down. So negative coefficient and even degree. And what's the smallest minimum possible degree for this polynomial function here? It has to be 4 because the end of it behavior is the same. If I look at the number of x-intercepts here, okay, we only had 3. Could have had at most 4. Number of turning points is n minus 1. So 4 minus 1 does give me the 3 here, so 4 does make sense. Just going to be a 4. It says it's a quartic function, the only thing it could be for the minimum. Let's complete the graph of the polynomial function shown. Determine the number of x-intercepts. Well, look here. Got 1. This one just has 1. Okay, the number of turning points. Now, this one doesn't turn at all. It It stays the same direction whole time, just slows down a little bit. So we don't have any turning points on this one. Is the leading coefficient positive or negative? Well, it's going down to the right, so it's probably negative. And is it even or odd? In behavior here is opposite, so it's odd. So it's a negative coefficient with an odd degree. What's the minimum possible degree here? Now the numbers would lead us to believe that maybe the minimum possible degree is 1. But we know in order for the degree to be 1, it has to be a perfectly straight linear line. And it's not a perfectly straight linear line. So we have to go up to the next odd term, which would be a 3. Minimum possible degree here, 3. Okay. The complete graph of the polynomial function is shown. Let's determine the number of x-intercepts on this one. Well, it looks like 3. 1 here, 1 here, 1 here, 3 x-intercepts. Look at the number of turning points here. Got a turning point here, turning point here. So 2 turning points. Leading coefficient positive or negative. It goes up to the right, so it's positive. And is the degree of the polynomial odd or even? Well, you got opposite in behavior here, so it's odd. All right, minimum possible degree for this one is going to be 3, because obviously not a straight line. Okay. At most, 3 x-intercepts and n-1 turning points here gives you the 2. So 3 would make sense here for the minimum possible degree. All right, let's look at factors, zeros, intercepts, and solutions. So if p of x equals x minus 1 times x plus 2 times x plus 5, let's find the zeros of p of x, the solutions of p of x equals 0, and the x-intercepts of the graph of y equals p of x. Little secret here, they're all asking for the same thing. All I'm going to do to find the zeros of p of x is let p of x be 0. Set this whole thing equal here. Alright, same thing. If I was to find the solutions of p of x, I'm just letting p of x be 0. And if I'm finding the x-intercepts of the graph y equals p of x, I'm just letting it equal 0. So all 3 are asking the same question. I just have to solve here. Do that by setting x minus 1 equal to 0, x plus 2 equal to 0, and x plus 5 equal to 0. Okay, so here I have x equals 1, x equals negative 2, and x equals negative 5. So those are my 3 solutions to this problem for all 3 parts, A, B, and C, because they're all 3 essentially asking for the same thing. All right, let's look at this example. It says cost. The total cost of producing a product is given by the function c of x equals x to the third minus 12x squared plus 3x plus 9 $1,000, where x is the number of 100 units produced. How many units must be produced to give a total cost of $45,000? All right, now here's the key here. This function itself is in thousands of dollars. We want it to be $45,000, and actually what that means here is that I need to let this c of x function equal 45, not 45,000 because the function is already in thousands. So we're going to do 45 equals x to the third minus 12x squared plus 3x plus 9. Then to solve it algebraically, I'm subtracting the 45 over here. I'm getting x to the third equals 0 minus 12x here plus a 3x and then minus 36. Now what we're going to want to do is we're going to want to solve this by factoring by grouping because we're familiar with that technique. Okay, in the first one, I'm going to pull out an x squared. It's going to leave me with an x minus 12. And the second one, I'm pulling out a 3. It's going to leave me with an x minus 12. So that when I go ahead and factor completely here, it's going to be an x minus 12 times an x squared plus 3. All right, so we're to this step here. Now we're letting x minus 12 equal 0. We're letting x squared plus 3 equal 0. So that x equals 12 is a solution to our equation. And x squared equals negative 3. Okay, we take the square root of both sides. Need to add the plus or minus, but we have a negative in here, so we're really just looking at plus or minus I square root 3. This is a word problem talking about cost. We're not going to have these imaginary numbers in our cost function, so the only one that makes sense here is the x equals 12. This solution does not make sense in terms of our word problem. Okay. Now keep in mind that x is the number of hundreds of units produced. Okay, x is the number of hundreds of units produced. So we're not just looking at an answer of 12. Okay, we are looking at an answer of 1200. Okay, so because no real number x can satisfy the x squared minus or x squared equals negative 3, the only solution is 1200 units. Thus, producing 1200 units gives a total cost of $45,000. this being our actual solution, or if written in words, just 1200. Now, we've looked at the root method in other aspects, but here we're going to look at the root method in terms of larger exponents. So it says the real solutions of the equation x raised to the n equals c are found by taking the nth root of both sides. If x equals the nth root of c is if n is odd, and x equals plus or minus the nth root of c if n is even and c is greater than or equal to 0. Okay. All right, so let's do some examples. Okay. I don't have to worry about taking the odd root of a negative because we can take the odd root of a negative. So just kind of think in terms of that. If I take an odd root, I also don't have to add plus or minus because I can take the odd root of a negative here, and it's not going to give me a dual solution when I take an odd root regardless if it's positive or negative. Okay, well, let's look at it. I've got x to the third equals 125. So essentially what I'm doing here is I'm taking the cube root of 125. Cube root of 125 is 5. If you have problems and struggle with taking the cube roots, your TI calculator will do that for you. It's under the math, and then you scroll down and it has the cube root option. Let's look at B. Okay, with B, I got 5x to the fourth equals 80. I'm going to divide by 5 to start with. That's going to give me the x to the fourth equals 16. I'm going to take plus or minus the fourth root of 16 of both sides. So I'm getting x equals plus or minus the fourth root of 16. Fourth root of 16 is 2. Like I said, if you're not good with roots here, what we're going to want to do is we're going to want to use our TI calculator. If you go math and then you scroll down to the x root, hit the x root button, it'll let you put a 4 in the root area and then a 16 underneath the root to solve for it if you need additional help from your calculator. Now if we look at C, which is 4x squared equals 18, I'm going to start out by dividing by 4. I reduce my fraction of 18 fourths to 9 halves. So I get x squared equals 9 halves. I take the square root of both sides, do a plus or minus here because I'm taking an even number root. 9 does have a square root. Square root of 9 is 3. 2 doesn't have a square root or an easy square root there, perfect square. So I just leave it as the square root of 2. So my solution to this one, plus or minus 3 square root 2. All right, let's look at this one. It says the number of women in the workforce for selected years from 1950 and projected to 2050 can be modeled by y equals 0.00358 x to the fourth minus 0.783 x to the third plus 50.1 x squared minus 24.8 x plus 18,600, where y is in thousands and x is equal to the number of years after 1950. If the model remains accurate, when is the number of women in the workforce projected to reach 92.12 million? Now, a few keys here. Y is in thousands. But I'll be darned if they didn't give us the number that we're supposed to have in millions. So we got to do a little bit of a conversion there. Also to take note, x is equal to the number of years after 1950. So we're going to have a year conversion as well. Now, when we do this initial conversion from 92.12 million to 1,000, if we kind of look at a layout here, let's take an easy, let's just write it, 92.12 million. I'm going to actually write it as a number, so it looks like that's 92,120,000. If I'm converting it to thousands, my decimal needs to go with that thousands common point is here. So that's why it converts it to 92,120 thousands. I set that now equal to the equation they give me. Okay. Now, if I set that equal to the equation they give me, then I have the whole setup. 92,120 equals 0.00358 x to the fourth minus 0.783 x to the third plus 50.1 x squared minus 24.8 x plus 18,600. Now on my TI calculator, I'm going to let y1 be the 92,120, and I'm going to let the y2 be the 0.00358 x to the fourth minus 0.783 x to the third plus 50.1 x squared minus 24.8 x plus 18,600. Okay, so that's what I've got going on there. Now, if I graph both of these together, I should get a graph. If I zoom, I can get a graph that looks like this. Okay, you can kind of see that I've got my my y-axis from 0 to 100,000. I've got my x-axis from 0 to 110 if you want the exact same graph. What I'm looking to do, you can tell it on the screen here, I'm looking to find the intersection point. So I'm going to do second calc intersect and first curve, second curve guess. The only thing with this one you have to be a little bit careful, we're only worried about the positive values here, which is why I have the graph the way it is here. We're only worried about the positive values. It does actually have a secondary intersection point over here in the negative values, but we're not worried about those in this case in this word problem because we're going forward in time, not backwards in time. And if I find this intersection point on my calculator, this intersection point actually turns out to be x equals 100. Okay. Now we know that, hey, 100 isn't exactly the answer. We have to do a conversion here because x is, if you go back up here, x is the number of years after 1950. So 100 years after 1950 will give us the year 2050. So the number of women in the workforce is projected to reach 92.12 million in 2050. And there we have it. That completes chapter 6.3. If you have any questions, send me an email, no problem. Give your homework a try. If you have any problems, let me know. I'm here for you. And that completes the lecture. I will see y'all next time.